Hello everyone, welcome back. In this video we're going to solve another type of example that we have it based on density. Now at the end of the book we have problems that you can always refer to them to test your knowledge to see whether you'll be able to solve them or not. Now for density competition I'm going to solve just one simple one, 3.8. It says calculate the radius of an iridium atom given that iridium has an FCC crystal structure, a density of 22.4 gram per centimeter cube, and an atomic weight of 192.2 gram per mole. Now this time we have the density. As I said, we're using the density to calculate something else on the crystal structure. Now let's change the crystal structure to be BCC. I mean 3.8, 3.9, they are the same, but let's choose the BCC crystal structure. It says calculate the radius of vanadium atom given that vanadium has BCC crystal structure, a density of 5.96 gram per centimeter cube, and atomic weight of 50.9 gram per mole. We did for FCC, let's check this one to be BCC. So calculating radius of the atom comes inside Vc. Remember, it comes inside the volume of a unit cell, which is equal to a cube. So let's find the volume of the cube, then I can find. Why? Because I know that this is BCC crystal structure. Since BCC crystal structure, we know A is equal to 4 over root 3 R. So if I have the volume, I can calculate I can calculate R within the volume. This is what we have to do. Well, going to the equation, density is equal to N A Vc Avogadro number. Again, you know that N is going to be 2. The 2 come from where? 2 atoms, because we have BCC crystal structure. Vc, we're gonna let it like this. We can directly put this one inside here and find A directly. But let's make it shorter. We'll find Vc, then we'll go for the other one. A, we know what is given because of the vanadium, the elements we know, so A is given to us. This is A, and also the density is given to me. The density also is given to me to be 5.96 gram per centimeter cube. Now let's A we already know it. So if I write those things down, write them down, and we'll see the units, to see if we have to change anything or not. Well, density is 5.96. This is gram per centimeter in units. Then N, it's 2 atoms. Atomic weight, it's 50.9 gram per mole, this one. And at the bottom I want to calculate Vc. Avogadro number is atoms per mole, 6.22 10 to power 23. So the units for this one, it's gram per centimeter cube, because I need to know what will be the unit of the volume. This is atoms, we said. This is gonna be gram per mole. So where does those things goes? And we have this one, atoms per mole, atom per mole, and we know this is atom. This 2 is going to be number of atom. So if you check them, atom will cancel atom here, mole will cancel mole here, the gram will cancel the gram here, then we have centimeter remaining for this, which means that the volume of the cube, or the volume of the unit cell, will be in the measure of centimeter cube. Centimeter cube will come as centimeter cube. Well, I will leave it like this first. I will find even r as the centimeter, but we know that the radius of atoms are very, very small. We'll always represent them as nanometer. So at the ends, I can change it to nanometer. So if I calculate volume of this unit cell from this calculation, based on what we have it here, it's going to be something very small. Write it down here. It's going to be 2.836. I'll make this one 4. That's enough. 10 to power minus 23 minus 3 centimeter cube. Now we know that 1 centimeter is equal to 10 to power 7 nanometer. This is the base we have it. I hope you know those units. Nanometer. Then if I cube this 1 centimeter cube, in that case we're gonna have 10 to power 21 nanometer. So if I want to change this one to nanometer, I will multiply it by 10 to power 21. So 21 with 23, that's going to be 10 to power. So if I bring this one back here, it will be 2.8364 10 to power minus 2 nanometer cube, multiplied by 10 to power 21. So we can rewrite this one even in a shorter version for us. 0.028364, like this, nanometer cube. This is the volume. We have it. Now we know volume is equal to a cube. So I can get a from here. Why? Because this is the volume. Yes, it just goes somewhere empty. Okay. So we found the volume. To be 0.02834 nanometer cube. I'm gonna go find a, because we know that v is equal to a cube. So if I want to find, I'll take root 3 for this side and root 3 for the volume, which is 0.028364. Then in that case we got a. I'm gonna step by step to make it easier to find r. So we're gonna take root 3 of this one. Look, simple calculation, but you have to know how to find it. So a is gonna be 0.30497 nanometer. And we know, because we have BCC, because of BCC crystal structure, we have it there, A is equal to 4 over 3 root 3 R. Then R will be root 3 times A divided by 4. So since we have A, we can calculate. Now we will check if you have any mistake. Now R, we found it to be 0.132 nanometer. You simply brought A back into here, times root 3 over 4 can give us 1.132 nanometer. Now if I check the table for vanadium, we have to get something close to this atomic radius, 0.132. If you haven't done any, well, basically I did the calculations. If I haven't done any mistake in the calculation, we shall see the result soon. Now we'll check vanadium here. That will be somewhere here, vanadium, and atomic radius 0.132. That's going to stand for atomic radius, so it is 0.132, and we calculated 0.132 based on what? Based on having the density, and we know the element, we can calculate the radius. Why? Because that will be enough. You know the crystal structure, you have everything to calculate the radius of atom. Now this was an example here. Based on having the density, you calculate the radius of the atom. Or sometimes you can find, we've already found A, found volume of the unit cell, and then A, the lattice parameter, and we found R. So by knowing density and the crystal structure, you can find all of this information related to the crystal structure. In the next video, we're gonna solve an example, which is we want to find its crystal structure. So whether 3.13 or 3.14, we're going to tell you how we're dealing with this type of example, which is the third way of using density computation that we will find the crystal structure. Thanks for watching.